Hi, I'm Kartik, and this is Lab 5, Faraday's Law. Here's a quick outline of what I'll go over in this lab. We'll start with the intro, where I talk about the purpose and the principles of physics used in this lab. Then I'll show you how I did this lab in the procedure section, and show you the results of the actual experiment, along with the VPython simulation, and check for accuracy. Finally, I'll conclude this report and provide a check for reasonability. The purpose of this lab is to explore why a magnet falling through a non-ferrous tube would be different than just free fall. We can relate the magnetic field of a falling magnet with time to a Curly electric field around the non-ferrous tube. Hopefully, we will be able to see that this will create a current which will create a magnetic field opposing the direction the magnet's falling. Finally, we want to better understand Lenz's law and Faraday's law. Faraday's law is the main principle of physics applied in this lab. It says that when the magnetic flux linking a circuit changes, an electromotive force, an EMF, is induced in the circuit proportional to the rate of change of the flux. Newton's third law says that the force an object exerts on another object is equal and opposite to the force exerted by the second object on the first object. Newton's second law says that the acceleration of an object is dependent on the force of an object and the mass of that object. The Biot-Savart law describes the magnetic field created by a current carrying wire. Finally, Lenz's law, in the case of this lab, shows that when we drop a magnet through a non-ferrous tube, it induces an electric field which generates a magnetic field in the opposite direction that the magnet's falling. To do this lab, you will need a roll of aluminum foil, a bar magnet, your smartphone, and a tool for measuring the dimensions of the tube. Mark the north pole of the bar magnet using magnetometer, then film yourself dropping the magnet through the tube. Use the footage you record to calculate the time it took the magnet to fall through the tube. Do this experiment twice, once with the north pole facing down and once with the south pole facing down. Now on to my measurements. I measured that the tube was 0.306 meters long, the foil was 0.012 meters wide, and the inner radius of the tube was 0.023 meters. I transplanted the value of 1.737 for the magnetic dipole moment of our bar magnet from Lab 3. I won't read out every time measurement, but there didn't seem to be a significant difference between having the north or south pole facing down, and the average time the magnet took to fall through the tube was 1.37 seconds. I also created a model of this experiment in VPython with the help of the starter code, and got that the magnet should take around 0.951 seconds to fall through a tube of this length and this thickness. Finally, to answer the questions from this lab report, if the resistivity of the conductor was reduced as close as possible to zero, the magnet would fall slower at a constant speed as the magnitude of the upward magnetic force would increase. If there were holes cut into the tube, there would be less magnetic force along the non-ferrous tube, so the magnet would fall much faster. You couldn't do this experiment with a ferrous tube, as there would be a magnetic field between the tube and the magnet, which would cause it to stick to the sides and wouldn't help us understand Lenz's or Faraday's law. Finally, for a reasonability check, there was a difference of around 30.5% or 0.419 seconds between the simulated values and the average of the actual values. These values aren't very precise, but they were definitely within the realm of possibility if things like air resistance and other external magnetic fields were properly taken into account. Thank you for listening to my lab, and have a good summer.